In the previous video, I worked out the canonical transformation or at least the conditions to show that our variables are going to work with a canonical transformation of the Hamiltonian. And I did that starting with one of Hamilton's equations, which says that the velocity in any frame of reference, if the variables are canonical, should be the derivative of the Hamiltonian with respect to the momentum. All right. So what I would like to do now is try it with Hamilton's other equation. So if I was the other one of Hamilton's equations, basically stated that the change in the momentum, I'll call this J, is the derivative of the Hamiltonian with respect to position. So if I have a Hamiltonian, I take the derivative of it with respect to position, I should get the time derivative of the momentum, basically the force. I should get the force out of it. So why don't we take a look at that? Let's try and work through it and show that we get the same canonical transformation from it. So if I start with this equation, this p bar dot is the time derivative of the momentum in the barred frame of reference, which is, I could also calculate that from the Poisson bracket of the momentum with the Hamiltonian. And again, the Hamiltonian in this case is a Hamiltonian in the barred system. So after there's been a transformation of the coordinates. And so I could write this out as the sum. So let me go back. Let me get rid of that. And now let me write out the sum of, basically let me write out the Poisson bracket of the momentum, J, with respect to Q, and the Hamiltonian, take the derivative of that with respect to momentum, minus the derivative of the momentum in the barred system with respect to the momentum in the unbarred system, and the derivative of the Hamiltonian with respect to position. Okay. And so now what I'm going to do is I'm going to use the results from the previous video and substitute in for these Hamiltonians, the derivative of the Hamiltonian with respect to the momentum and position. Let me go back and fix that. So oh, no, that was right. So this one is the momentum, and this is the position. Okay. So now that I got that straightened out. So what I want to do now is to substitute out these derivatives of the Hamiltonian with respect to momentum and position in the original frame of reference, to get them in terms of derivatives in terms of the barred or transformed frame of reference. So you have to go back and look at the previous video, but if I do that substitution, I'm going to sum over I, and then sum over the index k, and then I get the derivative of the barred momentum with respect to the unbarred position. Now we substitute out for that derivative, and that is the derivative of the Hamiltonian with respect to the barred position. sub k, so that's where the k index comes in, and then the derivative of the barred position with respect to the unbarred momentum plus derivative of the Hamiltonian with respect to the barred momentum, and then the Jacobian. So basically what this is all that's in that square bracket is taking that Hamiltonian, which is now with the derivative of the Hamiltonian with, say, P, the momentum in the original frame of reference, and then doing a transformation. I'm changing from the unbarred frame of reference into the barred frame of reference. Okay, so let's do that for the other derivative of the Hamiltonian. So I get not plus, but I get minus derivative of the barred momentum with respect to the unbarred momentum times, if we now do a change of reference, okay, there we go. So again, all I've done is to replace these derivatives that the derivatives are with respect to the original frame of reference, and then I've just done a transformation. So now I have derivatives with respect to the barred frame of reference right here, and I have to multiply them through the chain rule with these derivatives that move from the barred observable into the unbarred observable. Okay, so let's clean it up. So let's now group together the derivatives of the Hamiltonian. So this one will be dh d q bar, and when I do that I get d p bar j dqi dq bar sub k over dpi minus that would be dp bar j over dpi dq bar k over dqi. Okay. And so now, not to jump ahead, but if you remember from the previous video, that's going to be the Poisson bracket. So let me write out the other term first. So the derivative of the Hamiltonian with respect to the momentum bar is going to be d p bar j over dqi dp bar sub k dpi minus dp bar j dpi dp bar k over dqi. All of that is summed. Okay, so now if we take the sum over the index k, then you can see the Poisson brackets. I'm sorry, take the sum over the index I, because that's the I is the one of those unbarred variables in the denominators. So if we sum over I, we get derivative of the Hamiltonian with respect to q bar sub k, the Poisson bracket of p bar j q bar k plus the derivative of the Hamiltonian with respect to momentum bar, and this is the momentum bar J and the momentum bar K, that Poisson bracket. And remember that, if this thing is conserved, then, well, no, it's not conserved. Now what we want to do is use the identities of these Poisson brackets to clean things up. And so the Poisson bracket of P and Q is the Kronecker delta, and the Poisson bracket of the momentum with another component of momentum is 0. So if that is the case, then the time derivative of P bar J is the sum of K, the derivative of H with respect to position, Q bar, times the Kronecker delta JK. We sum over K, and we basically get the derivative of the Hamiltonian with respect to position in the barred system. So again, we return to one of Hamilton's equations. And that was possible because the canonical transformation keeps these Poisson brackets intact. And from the previous video, the same thing is true with the position components. The Poisson bracket of the positions is 0. So that leaves us with this condition. This is the condition now to ensure that there is a canonical transformation. If you apply those Poisson brackets either in the original frame of reference, which we called Q and P, or in the transformed frame of reference P bar, Q bar, then if these Poisson brackets give these results, then we're confident that the transformed coordinates are going to be valid, and Hamilton's equations are going to remain valid.